chapter 6 in the text. And of course, there have been some rather interesting developments since this book was printed, and I will present, in fact, you have a handout already of 3 figures there of data that has been made available since that, and we will discuss that. Now, when we're looking at the grapevine, and knowing now, hopefully, the structure of it, what's happening inside of it, let's first think of water. The vines will use somewhere from 15 to 50 acre inches per year. In other words, if the water were suddenly put on the vineyard, it would be anywhere from 15 to 50 inches deep over a 12-month period. This, of course, takes into consideration in evaporation, water losses through trickling, and so forth. So the vine does have a wide range in which it can function. Of course, its productivity is going to be affected. You have a question?
What would be a main variable on that? Evaporation would be a main variable?
Tremendous variable, yes. And the porosity of the soil, water that will trickle away, you see, into the groundwater stream. And then, of course, the big variable, I meant evaporation not only from the soil, but also from the vine itself, which is a bigger factor, actually, by far a larger factor. Now, the productivity is going to be affected by, depending on whether the water is plentiful or not. We interpret the 50 inches as being as plentiful, and the 15 as being considerably less than that. Water moves very fast through the vine. It's been calculated that it will move as fast as 30 feet per hour through the xylem tissue under conditions of rapid transpiration from the leaves. That figures out, I think, to about an inch in a minute or something like that. So it's a pretty fast rate, really. Or 6 inches a minute, something of that order. Those of you that are faster on math than I can figure that one out. Now, in order to appreciate this, we should have a little concept of vapor pressure difference or deficit. We can think of any living tissue in the vine as being essentially a saturated condition. In other words, where there's any air spaces between the cells. This is particularly in the leaves now we have reference to. You have either liquid water or essentially a saturated condition. So that usually always, outside of the vine, it's going to be less than this, and therefore there's always usually always the tendency for the water vapor in the vine to move to the surfaces and be evaporated. And of course, the velocity of this physical phenomena varies enormously depending on the difference. We have this saturated condition in the vine, and we have less than saturated, usually always, outside. Now, one further factor, this so-called escape tendency of the water vapor in the vine is directly proportional to temperature. So the warmer this tissue is, therefore the greater the vapor pressure of the water, the faster the tendency to escape. And this, of course, is the physical phenomena that we're concerned with in transpiration rates from the vine, and then in terms of the root system that has to supply this water, whether it's in balance with the leaf system on the top. And here vineyard management gets very, very important, is very important. For example, we mentioned the operation of girdling of a grapevine for various reasons, chiefly to increase berry size in Thompsons, advance maturity in some of the colored varieties. This, of course, cuts off temporarily, if done properly, the phloem tissue or the translocation to the roots. Root growth immediately stops. Now, the main absorption area of the roots, of course, is right at the tips, the tender little epidermal cells before any of the cork formation has taken place, or the root hairs just behind it, which again are actually extensions of epidermal cells. These don't live very long, and if there is no growth, these eventually senesce within a matter of days or weeks and die. And of course, then the absorptive surface of that vine is drastically reduced, and it's reduced rapidly. And of course, if the food materials are cut off, growth ceases. The vine then is living temporarily on just what it's got with it, so to speak. And usually that time of the year, the nutrients are depleted drastically, as we'll see in some of these handouts. So girdling then has to be used judiciously, partly because of the transpiration stream, this water balance. You cut off the water supply. Then if you'd get aggravating conditions of hot, dry weather, wind too, you can put the vine into a very serious condition of stress. Mother Nature can do this every now and then too. If you have a long period of rather cool weather, you don't have these severe conditions. It's warm enough though for rapid vegetative growth. The shoots are elongating at a terrific rate. Leaf area is expanding and probably taking place at a faster rate than corresponding root growth in the ground. Then suddenly comes a very hot condition. Then you have this tremendous vapor pressure gradient situation, and the vine can go into a very serious condition of water stress simply because the transpiration surface demand exceeds the supply. And this can be reflected in sudden cessation of growth, wilting, and it can even result in dehydration of the fruit. It's been demonstrated many times with many plants, and this is true of grapevines too, that if the transpiration demand, the evaporation, is greater than the supply, that evaporation will be supplied at the expense of the fruit. A classic demonstration in plant physiology is to take a branch of an orange tree, since you've got a fruit that's big enough to see quite easily, with a lot of leaves, cut it off, versus a branch where you cut off the branch but take off the leaves. The branch with the leaves, the fruit will become soft and shrivel, much more so than the fruit on that branch where the leaves have been taken off. So the lesson obviously is that the water is moving from the fruit through the stem structure to the leaves and being evaporated. So this balance between the roots and the vine then is quite important, between the roots and the leaves. Where is the water lost? Primarily through the stomates. They're very thick on the undersides of the leaves, to some extent on the upper surface. It's in some ways a necessary evil to the vine because it's through those same stomates that the CO2 has to diffuse in for photosynthesis and the oxygen diffuse out. And then of course in respiration, the reverse. And of course, during that time, naturally water vapor is going to also move through these stomates. It doesn't take many stomates on a leaf to be very potent. They say that if the stomates are evenly divided on a leaf, distributed, even though the actual opening of the stomates, if you could figure all of the cross-sectional area of the open stomates, is only 1% of the total surface of the leaf, the transpiration capacity of those stomates is about half that of a free water surface, yet only 1%. And the reason being, you see, that as you diffuse out through a small opening, if you can go along with me and call this a stomate, guard cells, as the water diffuses out, it has an opportunity here to immediately diffuse laterally as well as upward. And here's another stomate over here, and it can do likewise. The fact that it can diffuse very quickly laterally increases the rate per unit area of open surface where water can evaporate, water vapor can evaporate from a stomate. So even though the actual openable area is quite small, or appears to be, say 1% on a leaf, the water loss rate from those stomates is unexpectedly high, as much as 50% of the rate at which water would evaporate from a free surface. See, from a free surface, this would be all water, no chance to laterally evaporate from any kind of an opening. It all has to go straight up. Therein is one of the reasons for this tremendous rate of transpiration associated with the per unit area of open stomates. Now there are modifying conditions. Stomates may close in response to wind. You might even have in wind a slowing down of transpiration if the response of the stomates is to close. Normally we think of wind aggravating it because it blows away the water vapor film and of course then increases your gradient and therefore the steepness of the gradient and therefore the tendency for the leaf to lose water.
Doesn't high temperature also?
High temperature, yes, that's right. Stress usually will cause stomates to close. And this could be heat, as well as perhaps wind, severe wind, and of course a wilting condition. And usually this is a defensive mechanism of the plant. If the water deficiency is such in the plant that the transpiration has exceeded the supply, then of course the cells become soft, they will collapse, and in many plants, of course, there's a very active rolling of the leaves, for example, to cut down surface. Not in the grapevine. As a matter of fact, the grapevine can take a tremendous amount of punishment before you really see the symptoms very plainly. The damage is there, and that's why the viticulturist has to be quite alert. The vine has been drastically reduced in efficiency before you have distress symptoms that are quite obvious. And that's why our viticulturists should be, and many are, very conscious of water management in the vineyard. You're operating basically between what is called the permanent wilting percentage of the soil in terms of water content and field capacity. In other words, you can add water to a given soil to a point, and then from then on it won't hold anymore, it simply drains away, field capacity. Now that doesn't mean completely saturated. It has air spaces and so forth in it. It just means that's all that that soil can hold. Now the plant will extract water from that down to a point where it can no longer extract moisture from that soil. That is the permanent wilting percentage. The clever viticulturist is going to try and keep that soil certainly away from that permanent wilting percentage, because before the vine reaches that, its efficiency in terms of elaboration of carbohydrates particularly is considerably reduced. On the other hand, he wastes water if he tries to keep it above field capacity. So water management becomes very important. And fluctuations can do considerable harm in this short longevity of the root hairs and such as this. If you have violent fluctuations between high water content in the soil and permanent wilting percentage, then your root growth is irregular and erratic. Also, of course, too much water on the soil, if it's in a situation where it can't drain, then you are above field capacity. And if it's to the extent that the air is excluded from the soil, of course, this excludes oxygen. The roots, of course, need oxygen for respiration. And this can be carried to the point where the roots will actually die from anoxia, without oxygen. There have been vineyards killed by being submerged in water long enough. Now, the damage is not nearly as rapid if it's cold, such as in the wintertime. But when the temperatures are higher, respiration rates are higher, then this damage from lack of oxygen, of course, it comes on much sooner. Methods of absorption. Two main methods. There's the straight absorption by diffusion. If the ions are more concentrated in the soil than they are in the root, there's a translocation strictly by diffusion through the cell membranes and into the cells. Now diffusion there, this diffusion, however, is not simple physical. That is, there is a vital living force involved here because it has to be moved along, so to speak. The plant is removing ions by virtue of its living processes, and as they're removed, then the concentration gradient is set in, more ions come in, and this progressively goes along. Professor Winkler uses the illustration of an endless belt, pulling or carrying away the ions from the roots to the top part of the plant. The other method is where the ions can actually move against a gradient, and this certainly involves the energy derived from respiration, yes.
What ions are you moving now?
Well, it can be any kind. It could be the phosphorus, potassium, calcium, magnesium, any one of them. Well, both cations and anions for that matter, that are needed for the nutrition of the vine. Just go through the list of the elements that are needed, and these would be the ones, because essentially all of them normally come through the roots. It's true, we can add certain minerals by sprays on the vines, but this is an artificial thing, so to speak. Zinc can be applied, for example, to a grapevine by daubing it on the fresh wounds and pruning to correct a zinc deficiency condition. Iron, to a certain extent, can be also added with chelated compounds. But normally they come in through the roots. Now let us turn our attention to the forces in the leaf primarily, and that is this very interesting process, photosynthesis. I'm not enough of a biochemist to go into all the intermediary metabolism of photosynthesis, tracing it step by step from the basic compounds to the hexose sugar. Sufficient to say that if you combine 6 molecules of CO2 with 6 of water, you will derive 1 hexose sugar and 6 free oxygens. Now, there's one element in there that I haven't mentioned, and that's what makes it photosynthesis. It takes energy to do this, radiant energy. And for every mole of sugar, it takes about 673 calories. Now, I'm sure, well, I know all of the biochemists that are involved in this at all certainly would agree that it is not just this simple process. There are many intermediate steps that are involved in this overall process to put this radiant energy in 673 calories by virtue of using the chlorophyll, at least for some of the steps, in order to produce this hexose sugar, which is the basic unit of practically all metabolism. In fact, your respiration equation is just exactly in reverse. Combining the oxygen with the sugar, releasing this same amount of energy to give CO2 and water. These both processes can be going on in the same cell at the same time. Normally, in a green leaf, you will have this process dominating during the radiant energy periods, and of course, when there is no light, then the respiration process would dominate, because this leaf is continuing to grow. It has certain other vital functions to perform, and so you do have both processes going on. When we get over into the chemical composition of the fruit, then we'll go into a little more detail into the kinds of compounds that are elaborated and where they're translocated. Right now, I would like to draw your attention to what happens overall in a grapevine during the seasons. In this case, let's see how the light affects our photosynthesis activity. And you have a handout there of this particular transparency. Let's focus first on this one here, where we have net photosynthesis in terms of grams of CO2 utilized per decimeter, square decimeter, per hour. I forgot to put the superscript 2 there for that square decimeter. And in the last 10 years, this has been quite well worked out for the grapevine. Work done here. This is Australian results here. This was done with a Sultana field vine, which to us is the Thompson seedless, and also a Shiraz or Palomino vine here, both under field conditions, and this in a controlled shade house condition. sort of a phytotron type of facility. And it's rather interesting that once you get above about 5,000 foot candles, apparently you do not get any greater photosynthetic rate where light is the parameter that you're increasing. In other words, somewhere up in here, from there on. But it is also interesting that even if you double it or even treble it, you do not depress photosynthetic activity, except there's an indication here this might be experimental error. Under these control conditions, it looks like it's essentially reached its maximum level at about 5,000 foot candles and will not increase beyond that point. Yes?
Are these figures the same for all varieties?
Well, it would be unfair to say. There hasn't been enough information yet to say whether varieties will differ widely or not. My guess is probably they're not going to differ very much. No, if you're quoting it now on the basis of per unit area of the leaf. Now, of course, varieties vary tremendously in their vigor in how many leaves they put out and how big they are. If you were talking then about the total CO2 evolved from the vine, you see, or something like that, then we probably could get very great differences among varieties. But if you keep it on a per unit area of leaf basis, my theory is that probably not, at least very much. These two, incidentally, agree quite closely. Now let us look at where temperature is involved in the lower one. Now we do have a drastic effect on photosynthesis depending on the temperature, both if it's too low or too high. Below about 41 degrees Fahrenheit, there is essentially no formation of sugars, at least based on CO2. And it climbs rather steeply there to a maximum that occurs at about 77 degrees Fahrenheit. 78, I think it is, somewhere in that neighborhood. It's below 80. And then a very sharp drop-off in rate of photosynthetic activity as the temperature is increased beyond that point. Now you can see immediately the implications where we get into a fallacy with our degree day, where we would, it being, of course, mathematically, would be based on a linear basis, that this rate would continue on up, and it doesn't. Now, if we get into days that are 90, 100, 105 degrees.
Does that mean that like at 105 is zero activity across the stratum?
Probably if all that tissue were at that temperature, but as it turns out, not all parts of the vine are. What you're talking about is rate, you see. And during that actual time at, say, 100, well, actually you go down to, 100 degrees, say, Fahrenheit. Presumably that tissue, if it's at 100 degrees Fahrenheit, the interpretation would be that it is not, the rate is not increasing. In fact, it's depressed to where it's probably not producing any.
How close is the leaf temperature usually to the air temperature?
It varies. It's usually cooler. It's usually cooler because of the transpiration, the absorption of latent heat. It goes lower. The fruit many times can go higher because of the mass and the absorption of infrared with a lower surface to volume phenomena. And then you can get fruit temperature that's exposed to the sun that is higher than the actual air temperature around it. As long as it's in the shade, it's always lower, again, because of transpiration, at least for one factor. And leaves, because of their enormous number of stomata and water loss rates, usually always are lower. But this is some of the information that's now just coming out, you see. We get into this more critical evaluation of this grapevine in response to these factors of the environment. Temperature here is looking like a very, very important thing, and how are ways that perhaps we can avoid these temperatures when we don't want them. I see several hands up. I'll take them one at a time. Yes?
Wouldn't leave in direct sunlight on a day that's 90-degree air temperature, the leaf would be a lot hotter than 90 degrees.
A lot hotter?
Wouldn't it?
Not necessarily, because the equilibrium temperature, you can't call it equilibrium. Well, yes, it could be an equilibrium temperature in the leaf, is the sum total of several factors. The rate of absorption of the radiant energy, the rate of absorbing the cooling effect of the transpiration of the water vapor from it. The leaf does absorb a tremendous amount of that energy. As a matter of fact, the leaf will absorb about 90%. If you put one leaf below another, and the sun passes through the first leaf will intercept about 90% of that usable radiant energy in photosynthesis. And that leaves only 10% for the leaf underneath. And of course, if there's another leaf below that, he's in bad shape. And this, of course, gets into the implications of trellising and various other things to spread this vine out, so that it's true if you're exposing leaves to 10,000 foot candles, you could probably go through 2 or 3 leaves and still have enough for that leaf down here to be doing something. But even so, the spreading out and making the vine more efficient is now a very attractive way of going to make more sugar, more grapes, more wine. Yes?
Rate of foot candles were put on this vine that was done. Was it up 5,000 or 10,000? Was it constant?
Yes, well, you say constant. They controlled these parameters at least to the degree that they thought that these responses are valid. Most of this data is based on phytotron work. In other words, in a greenhouse where temperature can be controlled, light can be controlled. These are very major problems, believe me. And knowing these people that do this work, Professor Cleaver upstairs is one, and then these workers in Australia, they've been here and given seminars. They're very, very reliable research people. I have a lot of confidence in their data. And I think Professor Winkler has, because it's going to be in the next edition. Yes?
Of the energy absorbed by the leaf, how much is used in photosynthesis? In other words, how efficient is that?
Well, I could give that example, that the leaf exposed to the sun will intercept about 90% of the radiant energy. In other words, only 10% it gets through it, gets away.
Energy is wasted, though, in photosynthesis.
I can't give you the figures on the actual efficiency index, or whatever you want to call it, of the process itself. I don't know that. Yes?
Because the leaf stops the radiant energy doesn't mean that it's all absorbed, isn't a lot
That's
of
right.
it
That's right.
reflected?
That's right. That energy that is absorbed by that leaf, that 90%, part of it is re-radiated as heat. Part of it is picked up by the water and various other ways is re-radiated to the atmosphere. Yes, I don't interpret that 90% all goes into the photosynthesis. No, it does not. And to get down to the actual efficiency index for so many quanta of energy that goes into the leaf, what number actually are tied up into the reserve energy in this sugar molecule, that I don't know. Yes? I don't think they have studied enough varieties yet, to my knowledge, to be able to draw a conclusion on that. They have obviously picked varieties that were available, that they could control in various ways that lended themselves most convenient, particularly to phytotron activities. This involves growing them in pots, usually up to a certain stage in a greenhouse, before they go into this extremely expensive phytotron space for that critical study. Yes? I don't know, because I presume that they controlled these other factors and kept them constant so that they could say this, as you change this variable, other things being equal. Yes. It would be under conditions of, in the case of the lower one, temperature, constant illumination. Now, I would have to go back and find out just what the illumination level was for that bottom one. But as I recall, though, it would be a normal level of illumination, probably above this. Oh, it's up in the maximum rates.
No, but obviously, if there were very high humidity, unlike under greenhouse conditions,
possible, although they were measuring this temperature. This is leaf temperature now. This leaf temperature, oh yes. Thermistors that are placed right in the leaf itself. Oh yes, this is the tissue temperature of the leaf. Well, there again, it can vary depending on the radiant energy absorption, the rate of water loss from the leaves, you see?
To make that, to have this information really be useful, you have to have some basis for relating it to, because we don't, out in the field, we don't have basis against.
Well, oh, I think there is.
You said that like if it's 105 and 20% of your leaves are going to get 95 or something like that nature. Depends on the relative.
Well, there again, of course, you have enormous differences in exposure in a vine, depending on the. But oh yes, this is simply as a start. It's data like this that has excited this tremendous interest in using overhead sprinklers to lower the temperature of the vineyard during the summer. Now, the data is not all in on that as to whether by lowering the temperature of your vines a few degrees by supplying water externally, in other words, you're supplementing your transpiration cooling, and you can get several degrees of cooling of a vine. Now, is this now going to be reflected in the quality of the fruit, the balance of the compounds? It's too early yet to say. But this is what's excited that kind of work, because of this fear of this area over here. Well, I see the hour's up. I suppose if anyone has a... How many have a class the next period? Yeah, okay. Let's not hold them up. We can continue this discussion, because we didn't get over to this one over here, leaf age in terms of its, whether it's a parasite on the vine or whether it's an asset. Be sure and bring the, keep the handouts with you if you will, class, because we will discuss those.